Hi everyone. In this video we'll go over a new concept, which is the margin of error. In an earlier video I talked about the concept of the standard error. I said that the standard error shows how accurate the sample mean is likely to be. The standard error tells the researcher how close the sample mean is likely to be to the population mean in his or her study. The margin of error is really just another value that shows how accurate the sample mean is likely to be. However, the margin of error is interpreted a little bit differently than the standard error. In this video, we'll go through some examples of calculating the margin of error, but before we do that, I wanted to spend some time reviewing some concepts from some earlier videos. I want to review the standard error, the z-score of a sample mean, and the central limit theorem. I want to review these concepts because these concepts will be important when we talk about the margin of error later on. To help me explain these concepts, I made up a situation in which I'm a researcher who's interested in estimating the mean age of a population of 24,000 people. Unknown to me, the mean age of this population is 24, with a standard deviation of 8. Remember that mu is a symbol for population mean, and sigma is a symbol for population standard deviation. So, the population mean is 24, and the population standard deviation is 8. Let's think about what these two numbers are telling us. I think that the mean is the easier number to understand. The mean is just telling us that in this population, the average age is 24. The standard deviation is a little bit more challenging to understand. What the standard deviation is telling us is that in this population, the average distance to the mean of 24 is roughly 8. In other words, if you looked at all of the people in this population, most of the people would fall somewhere between 16 years old and 32 years old. Let's say that I decide to randomly select 4 people from this population. I decide to randomly select 4 people, record their ages, and then calculate the mean of those 4 ages to estimate the mean age of the population. I know that 4 seems like a pretty small sample size, but we'll just use 4 in this example. In order to get an idea of how accurate my sample mean is likely to be, I decide to calculate the standard error in my study. Since the population size is more than 20 times larger than my sample size, I can use the short standard error formula. The short standard error formula says to divide the population standard deviation by the square root of the sample size. Remember that little n is a symbol for sample size. I'm going to divide the population standard deviation of 8 by the square root of 4, which is my sample size, and then that'll give me my standard error. The square root of 4 is 2, so I'm just going to be dividing 8 by 2. 8 divided by 2 equals 4, so my standard error is 4. Let's think about what this number is telling me. This number is telling me that when I randomly select my sample of 4 people from the population, my sample mean is likely to be about 4 away from the population mean. In other words, my sample mean is likely to be about 4 off target. Now this standard error isn't telling me that my sample mean is definitely going to be 4 off target. It's just telling me that my sample mean is likely to be about 4 off target. The exact amount that my sample mean is off target by depends on which sample I end up selecting. You might be wondering how I would calculate the standard error in my study if I don't know what the population standard deviation equals. We'll actually talk about that situation in a different video. We'll talk about how a researcher who doesn't know what the population standard deviation equals will use a slightly different formula to calculate a value called an estimated standard error. However, in this video, we'll just pretend that I do know what the population standard deviation equals and that I can calculate the actual standard error. Now that we've reviewed the concept of the standard error, I'd like to go over the z-score of a sample mean. Let's look at the numbers on this number line and find the z-scores of some of these numbers. First, we have to realize that when the sample mean equals the population mean, the sample mean has a z-score of 0. In my example, the population has a mean of 24, so if my sample mean comes out to 24, then my sample mean will have a z-score of 0. If my sample mean comes out 1 standard error below the population mean, then my sample mean will have a z-score of -1. And if my sample mean comes out 1 standard error above the population mean, then my sample mean will have a z-score of +1. In my example, the standard error is 4. So if my sample mean comes out 4 below the population mean of 24, then my sample mean has a z-score of -1. If my sample mean comes out 4 above the population mean of 24, then my sample mean has a z-score of +1. In other words, if my sample mean comes out to 20, then my sample mean has a z-score of -1. And if my sample mean comes out to 28, then my sample mean has a z-score of +1. If my sample mean comes out 2 standard errors below the population mean, then my sample mean has a z-score of -2. And if my sample mean comes out 2 standard errors above the population mean, then my sample mean has a z-score of +2. In my example, the standard error is 4. So if my sample mean comes out 8 below the population mean, then my sample mean has a z-score of -2. And if my sample mean comes out 8 above the population mean, then my sample mean has a z-score of +2. In other words, if my sample mean comes out to 16, then my sample mean has a z-score of -2. And if my sample mean comes out to 32, then my sample mean has a z-score of +2. At this point, let's actually take a random sample of 4 people from the population. Once we take our sample of 4 people, we're going to record the ages of the 4 people in the sample, calculate the mean of the sample, and then find out what the z-score equals. Let's say that we randomly selected these 4 people to be our sample. I decided to give each person in the sample an ID number, and these are the ages of the 4 people in our sample. The mean age of this sample is 22. If you added these 4 ages and divided the total by 4, the answer would be 22. So x bar is 22. Remember that x bar is a symbol for sample mean. I put an x bar up here on the number line just so you could see how close our sample mean is to the population mean of 24. Let's see if we can figure out the z-score of our sample mean. There's a formula that can be used to calculate the z-score of a sample mean, but I want us to try to figure out the z-score just by looking at the number line. We can see that 24 has a z-score of 0, and 20 has a z-score of -1. 22 is halfway between those two numbers, so 22 has a z-score of -0.5. Our sample mean of 22 has a z-score of -0.5. Let's double check that answer using the z-score formula. We're going to take this sample mean of 22 and plug it into the z-score formula, and then we'll see that the z-score really is -0.5. This is the formula for the z-score of a sample mean. The z-score formula for a sample mean says to subtract the sample mean by the population mean, and then divide by the population standard deviation over the square root of the sample size. So I plugged in all 4 numbers. I plugged in our sample mean of 22, the population mean of 24, the population standard deviation of 8, and the sample size of 4. If we did the math, we would see that the z-score does come out to -0.5. So our sample mean of 22 does have a z-score of -0.5. Let's do this again with a different sample. I'm going to repeat my study and randomly select a new group of 4 people from the population. Just like last time, I'm going to record the ages of the 4 people and calculate the mean age of my sample to estimate the mean age of the population. This time, I selected these 4 people to be my sample. I changed their ID numbers so you could see that this is a different sample of 4 people. Even though person 173 was in the first sample, I decided to include this person in the second sample as well. I did that to show you that it's possible to select a person more than once when you do random sampling. If you're sampling from a large population, that's really unlikely to happen, but it can happen. Over here, I recorded each person's age. The mean of this sample is 24. If you added these 4 ages and divided the total by 4, the answer would be 26. So x bar is 26. Just by looking at the number line, we can see that our sample mean of 26 has a z-score of plus 0.5. 24 has a z-score of 0. 28 has a z-score of +1, and 26 is halfway between those two numbers. So we know that our sample mean of 26 has a z-score of positive 0.5. Just like last time, let's use the z-score formula to make sure that the z-score is correct. This time, we're going to plug our sample mean of 26 into the formula. These other three numbers will all stay the same because the population mean is still 24, the population standard deviation is still 8, and the sample size is still 4. If we did this math right here, the answer would come out to 0.5. So our sample mean of 26 does have a z-score of 0.5. I want to stop for a moment to make sure that you notice something on the screen. Our first sample mean was below the population mean, so it had a negative z-score. Our second sample mean was above the population mean, so it had a positive z-score. A sample mean below the population mean always has a negative z-score, and a sample mean above the population mean always has a positive z-score. I want to do a couple more of these examples with you just to show you how the z-score won't always come out to a nice number like negative 0.5 or 0.5. Let's say that I randomly select a third sample of 4 people, and I get these 4 people as my sample. This sample has a sample mean of 18.5. If you added these 4 ages and divided the total by 4, the answer would be 18.5. By looking at this number line, we can see that 18.5 is about halfway between 16 and 20. That means that our sample mean of 18.5 should have a z-score of about negative 1.5 or negative 1.5. However, our z-score won't be exactly negative 1.5 because this sample mean isn't exactly halfway between the two numbers. However, we can see that our sample mean will have a z-score close to negative 1.5. It would be too difficult for us to find out exactly what the z-score of this sample mean equals just by looking at the number line. So let's use the formula to get the z-score. We're going to plug our sample mean of 18.5 into the formula, and then these three numbers are still the same that they were before because the population mean is still 24, the population standard deviation is still 8, and our sample size is still 4. The formula says that our sample mean of 18.5 has a z-score of negative 1.375. And this z-score is pretty close to negative 1.5. And that makes sense because our sample mean is about halfway between 16 and 20. Let's select just one more sample of 4 people. So I'm going to repeat my study a 4th time with a new sample. This sample has a mean of 31.5. If you added these 4 ages and divided the total by 4, the answer would be 31.5. 31.5 is about halfway between 28 and 32. So our sample mean of 31.5 should have a z-score close to 1.5. Our sample mean won't have a z-score of exactly 1.5 because our sample mean isn't exactly halfway between 28 and 32, but our sample mean will have a z-score close to 1.5. Let's use the z-score formula to find out what the z-score of this sample mean equals exactly. So we're going to plug in our sample mean of 31.5 into the formula, and these 3 numbers will stay the same. And the formula says that our sample mean has a z-score of 1.875, which is somewhat close to 1.5. At this point, I want you to notice 2 things on the screen. First, just like before, I want you to notice how a sample mean below the population mean will have a negative z-score, and a sample mean above the population mean will have a positive z-score. Second, I want you to notice how a sample mean further below the population mean will have a bigger negative z-score, and a sample mean further above the population mean will have a bigger positive z-score. Overall, a z-score shows two things about the mean of a sample. First, it shows whether the sample mean is below or above the population mean. Second, it shows how far the sample mean is from the population mean. When a sample is selected from a population, the further the sample mean is from the population mean, the bigger the z-score will be. You can think of the z-score as measuring how extreme or off target the sample mean is. One thing I should mention at this point is that a researcher who is calculating a sample mean to estimate a population mean typically can't calculate the z-score of his or her sample. That's because the researcher doesn't have enough information to be able to calculate the z-score. In order to calculate the z-score of your sample mean, you have to know what the mean and standard deviation of the entire population equal, because those two values go into the formula for the z-score. The mean and standard deviation of the population are almost always unknown. To calculate them, the researcher would have to have data from all members of the population. Even though a researcher typically can't calculate the z-score of his or her sample, the z-score is still an important concept. We'll see why it's important later in this video. Now that we've reviewed z-scores, let's review the central limit theorem. The central limit theorem allows us to predict the shape of the sampling distribution. The central limit theorem says that when the population that's being sampled is normal, the sampling distribution will always be normal. And when the population being sampled is not normal, the sampling distribution will be roughly normal with a sample size of 30 or larger. In this example, I'm taking my sample of 4 people from a normal population, so my sampling distribution will be normal, even though I'm only selecting 4 people to be in my sample. When you're randomly selecting a sample from a normal population, the sampling distribution is always normal, no matter what the sample size is. This normal curve is showing my sampling distribution. It's showing all of the possible outcomes that I could end up getting in my study. In other words, it's showing the means of all possible samples of 4 people that I could select from this population when I do my random sampling of 4 people. Each time I randomly select a sample of 4 people from this population, and I calculate the mean of my sample mean is one of the sample means under this curve. For example, my first sample had a mean of 22, so that sample mean was one of the sample means over here. My second sample had a sample mean of 26, so that sample mean was one of the sample means over here. My third sample had a mean of 18.5, so that sample mean was one of the sample means over here. And my fourth sample had a sample mean of 31.5, so that sample mean was one of the sample means over here. Now that we've reviewed the idea of the central limit theorem, we can move on to discuss the margin of error. Let's start with the definition of the margin of error. The margin of error is the distance from the population mean to the lower and upper boundaries of a certain percentage of the sampling distribution. This definition might not seem clear right now, but it should be clear after we go through a few examples. We'll go through a few examples of calculating the margin of error, but before we do that, I wanted to go through a quick exercise to help us understand the definition of the margin of error. I want you to imagine an area under this curve that includes the middle 60% of the possible samples. I want you to imagine that that area has a lower boundary and an upper boundary. 20% of the possible samples are below the lower boundary, and 20% of the possible samples are above the upper boundary, and the middle 60% of the possible samples are between the two boundaries. So we have a 20% area, a 60% area, and a 20% area. Since this sampling distribution is normal, the distance from the population mean to the lower boundary of the middle 60% and the upper boundary of the middle 60% would be the same distance, and that distance would be called the 60% margin of error. The 60% margin of error is just the distance from the population mean to the lower boundary and the upper boundary of the middle 60% of the possible samples. Now I want you to imagine an area under this curve that includes the middle 80% of the possible samples. I want you to imagine that that area also has a lower boundary and an upper boundary. 10% of the possible samples are below the lower boundary, 10% of the possible samples are above the upper boundary, and the middle 80% of the possible samples are between the two boundaries. So we have a 10% area, a 10% area, and an 80% area. Once again, since the sampling distribution is normal, the distance from the population mean to the lower boundary and the distance from the population mean to the upper boundary will be the same distance. In this case, that distance would be called the 80% margin of error. The 80% margin of error is the distance from the population mean to the lower boundary and the upper boundary of the middle 80% of the possible samples. There's actually a different margin of error for every percentage. There's actually a formula that can be used to calculate the margin of error for any percentage. I'll show you that formula in just a second. First, I want to mention that the margin of error formula can only be used when the sampling distribution is normal, like it is on the screen right here. There are three situations in which the sampling distribution is normal and the margin of error formula can be used. The first situation is taking a small sample of less than 30 from a normal population, which is what I'm doing. The second situation is taking a large sample of 30 or more from a normal population. And the third situation is taking a large sample of 30 or more from a skewed population. Actually, the only situation in which the margin of error formula can't be used is taking a small sample of less than 30 from a skewed population. In that situation, the sampling distribution isn't normal, so the margin of error formula can't be used. This is the formula for the margin of error. It actually has two parts to it. This part is just the standard error. It's the same formula we have over here. It's the standard deviation of the population divided by the square root of the sample size. This part right here is called the confidence coefficient. It has to be looked up in a table. When I go to that table, I have to actually look up the confidence coefficient that goes along with the percentage that I'm using. For example, if I want to calculate the 60% margin of error, then I have to look up the correct confidence coefficient for the 60% margin of error. If I want to calculate the 70% margin of error, I have to look up the correct confidence coefficient for the 70% margin of error. There's a different confidence coefficient for every percentage, and I just have to look up the correct one for the margin of error that I want to calculate. I think this will all make sense once we go through a few examples of actually calculating the margin of error. For our first example, let's calculate the 70% margin of error. The first step would be to go to the table and look up the correct confidence coefficient. We would need to go to the table and look up the confidence coefficient for the 70% margin of error. If we went to that table, the table would tell us that the confidence coefficient that we need to use is 1.04. That means that all we have to do is plug 1.04 into this part of the formula right here and multiply it by the standard error, and we'll get the 70% margin of error. Before we calculate the 70% margin of error, I want to take a moment to explain why we would use 1.04 to calculate the 70% margin of error. It turns out that when the sampling distribution is normal, like it is right here, 70% of the possible samples fall between the z-score of negative 1.04 and 1.04. In other words, when the sampling distribution is normal, negative 1.04 is the lower boundary of the middle 70%, and 1.04 is the upper boundary of the middle 70%. Notice how I put negative 1.04 a little bit below negative 1, and I put 1.04 a little bit above 1. when the sampling distribution is normal, like it is here, this is the lower boundary of the middle 70%, and this is the upper boundary of the middle 70%. 70% of the possible samples are in this area, and the other 30% are evenly divided between the two tails. In other words, 15% of the possible samples are in here, and 15% of the possible samples are in here. When we calculate the 70% margin of error, what we're going to be calculating is the distance from the population mean at the center to the lower boundary of the middle 70% and to the upper boundary of the middle 70%. The z-score that we're going to be plugging into the formula, which is 1.04, is just the z-score at the upper end of our middle area. So what I'm showing you right here is that the confidence coefficient is really just the z-score at the upper end of the middle area of the sampling distribution. And since we're calculating the 70% margin of error, the middle area that we're dealing with is the middle 70%. So let's plug this confidence coefficient into the margin of error formula and multiply it by the standard error, and then we'll get the 70% margin of error. So we plug in 1.04 right here. We multiply it by the standard error, which is what we have over here. The standard error is just the population standard deviation divided by the square root of the sample size. We know that the population standard deviation is 8, and our sample size is 4. There's actually 3 steps to calculating this. First, we have to find the square root of 4. Then we have to divide the fraction, and then we have to multiply this number by this number. The square root of 4 is 2. So we would divide 8 by 2, and 8 divided by 2 equals 4, like it is right here. So we're going to be multiplying 1.04 by 4, and the answer will be the 70% margin of error. If you multiply 1.04 by 4, the answer comes out to 4.2. So our 70% margin of error is 4.2. That means that the distance from the population mean to the lower end of the middle 70% of the possible samples is 4.2, and the distance from the population mean to the upper end of the middle 70% of the possible samples is 4.2. I want to spend a few moments talking about what this margin of error of 4.2 is actually telling us. It's really telling us 3 different things. First, it's telling us that if we randomly select a sample of 4 people from this population and record their ages, 70% of the possible samples that we could select would have a sample mean that's within 4.2 of the population mean in this middle area. 15% of the possible samples that we could select would have a sample mean out here, more than 4.2 below the population mean, and 15% of the possible samples that we could select would have a sample mean out here, more than 4.2 above the population mean. Second, this margin of error is telling us that if we randomly select a sample of 4 people from this population and record their ages, we have a 70% chance, or a 0.70 probability, of getting a sample mean within 4.2 of the population mean in this middle area. We have a 15% chance, or a 0.15 probability, of getting a sample mean more than 4.2 below the population mean out here. And we have a 15% chance, or a 0.15 probability, of getting a sample mean more than 4.2 above the population mean out here. Third, this margin of error is telling us that if we kept on randomly selecting different samples of 4 people from this population, and we kept calculating the sample mean each time, 70% of the time, we would get a sample mean within 4.2 of the population mean in this middle area. 15% of the time, we would get a sample mean more than 4.2 below the population mean out here. And 15% of the time, we would get a sample mean more than 4.2 above the population mean out here. So the 70% margin of error is telling us what percentage of the possible samples fall in each of these areas. It's telling us the probability of getting a sample mean in each of these three areas, and it's telling us what percentage of samples would fall in each area over time if we kept on randomly selecting more and more samples from the population using the same sample size. Now that we understand what this 70% margin of error is telling us, let's move on to calculating a different margin of error. Let's calculate the 90% margin of error. If we want to calculate the 90% margin of error, we would need to go back to the table and find the correct confidence coefficient to use to calculate the 90% margin of error. If we went to that table, it would tell us to use 1.645 as our confidence coefficient. The reason why it would tell us to use 1.645 is because when the sampling distribution is normal, like it is right here, 90% of the possible samples that could be selected from the population have a sample mean between these two z-scores, between negative 1.645 and 1.645. In other words, when the sampling distribution is normal, the lower boundary of the middle 90% is negative 1.645, and the upper boundary of the middle 90% is 1.645. I said that the confidence coefficient that you plug into this formula is really just the z-score at the upper end of the middle area. Since we're going to be calculating the 90% margin of error, the middle area that we're dealing with is the middle 90%. Therefore, our confidence coefficient is the z-score at the upper end of that middle 90% area. So let's take this confidence coefficient and plug it in to the formula and calculate the 90% margin of error. Once we get the 90% margin of error, that'll tell us the distance from the population mean to this boundary out here, and the distance from the population mean to this boundary out here. So we plug in 1.645, that's the correct confidence coefficient for the 90% margin of error. We multiply it by our standard error. Just like before, this will be three steps. First we have to find the square root, then we have to divide the fraction, and then we have to multiply the two numbers. The square root of 4 is 2, so we divide 8 by 2. 8 divided by 2 is 4, and then we multiply 1.645 by 4. When we do that, the answer comes out to 6.6, rounded. So the 90% margin of error, which is the distance from the population mean to the lower end and the middle end, to the lower end and the upper end of the middle 90%, is 6.6. Now let's think about what this 90% margin of error is telling us. Just like before, it's telling us three things. First, it's telling us that if we randomly select a sample of 4 people from this population and record their ages, 90% of the possible samples that we could select would have a sample mean within 6.6 of the population mean in this middle area. Only 5% of the possible samples would have a sample mean out here more than 6.6 below the population mean. And only 5% of the possible samples would have a sample mean out here more than 6.6 above the population mean. Second, it's telling us that if we randomly select a sample of 4 people from this population and record their ages, we have a 90% chance, or a 0.90 probability, of getting a sample mean within 6.6 of the population mean in this middle area. We have a 5% chance of getting a sample mean more than 6.6 below the population mean out here, and we have a 5% chance of getting a sample mean more than 6.6 above the population mean out here. Third, this margin of error is telling us that if we kept on randomly selecting more and more samples of 4 people, and we kept on calculating the mean of each one, 90% of the time, the sample mean would fall within 6.6 of the population mean in this middle area. 5% of the time, it would fall more than 6.6 below the population mean out here, and 5% of the time, it would fall more than 6.6 above the population mean out here. Now let's move on to calculate one more margin of error. Let's calculate the 95% margin of error. It turns out that when the sampling distribution is normal, like it is here, 95% of the possible samples have sample means between these two z-scores, negative 1.96 and 1.96. So if we went back to that table and we looked up the confidence coefficient for the 95% margin of error, it would tell us to use 1.96. So when the sampling distribution is normal, 95% of the possible samples fall in this middle area right here, and the other 5% is evenly divided between these two tails out here and out here. 5% divided by 2 is 2.5. That's why you have 2.5% here and 2.5% out here. So let's plug in this confidence coefficient of 1.96 into the formula, and then multiply it by the standard error, and we'll get the 95% margin of error. Remember that this part right here equals 4. We already figured out what it equals, so we're just going to multiply 1.96 by 4. 1.96 times 4 is 7.8. So that's our 95% margin of error. The distance from the population mean to the lower boundary of the middle 95% and to the upper boundary of the middle 95% is 7.8. This boundary is 7.8 below the population mean, and this boundary is 7.8 above the population mean. And this margin of error is telling us that, well, it's telling us that if we randomly select 4 people from this population and record their ages, 95% of the possible samples would have a sample mean within 7.8 of the population mean in this middle area. Only 2.5% of the possible samples would give us a sample mean out here, more than 7.8 below the population mean, and only 2.5% of the possible samples would give us a sample mean out here, more than 7.8 above the population mean. It's also telling us that when we randomly select a sample of 4 people from the population and record their ages, we have a 95% chance of getting a sample mean within 7.8 of the population mean. We have a 2.5% chance of getting a sample mean more than 7.8 below the population mean. We have a 2.5% chance of getting a sample mean more than 7.8 above the population mean. Finally, this margin of error is telling us that if we kept on randomly selecting more and more samples of 4 people from this population and kept on calculating the mean of each one, we would expect to get a sample mean within 7.8 of the population mean 95% of the time. We would expect to get a sample mean more than 7.8 below the population mean 2.5% of the time, and we would expect to get a sample mean more than 7.8 above the population mean 2.5% of the time. Now that we've gone through 3 examples of calculating the margin of error, I want to spend a little more time talking about the meaning of the margin of error. The margin of error tells you how much accuracy you can expect a certain percentage of the time when you use a sample mean to estimate a population mean. What this 95% margin of error is telling me is that if I kept on repeating this study over and over again with the same sample size, I could expect my accuracy to be 7.8 or better 95% of the time. I would expect my accuracy to be worse than 7.8 only 5% of the time. You could think of the margin of error as being a limit to how much error will be made a certain percentage of the time. You could think of the margin of error as being a limit to how much error will be made a certain percentage of the time when you use a sample mean to estimate a population mean. This margin of error is telling me that if I repeated the study over and over again with the same sample size each time, 95% of the time, I would expect my error to be no more than 7.8. In other words, I would expect my error to be more than 7.8 only 5% of the time. I would expect my sample mean to be more than 7.8 off target only 5% of the time. Finally, I want to wrap up this video by talking about what affects the margin of error. I want to talk about what makes the margin of error smaller and what makes it larger. One thing that affects the margin of error is the population standard deviation, or the amount of spread or dispersion between the population members. Another thing that affects the margin of error is the sample size. And I want to go through an example to show you how the margin of error is affected by the population standard deviation, and then go through an example of how the margin of error is affected by the sample size. Let's imagine that instead of having a standard deviation of 8, our population has a standard deviation of only 6. In other words, our population has a little bit less spread or dispersion than it did before. If the population's standard deviation is only 6, that's going to change the margin of error. And I'll explain to you why it changes the margin of error. First, we need to notice that if the population standard deviation is only 6, the standard error is going to change. That's because instead of dividing 8 by the square root of 4, we'll be dividing 6 by the square root of 4. The square root of 4 is 2, and 6 divided by 2 is 3. So when the population standard deviation went down to 6, the standard error went down to 3. What that's telling us is that when we randomly select a sample of 4 people from this population and we calculate the sample mean, we can expect the sample mean to be about 3 away from the population mean, instead of 4 away from the population mean, like before. Since the standard error went down, these z-scores are going to change. Because if the standard error is 3, a sample mean that's 3 above the population mean will have a z-score of +1, and a sample mean that's 3 below the population mean will have a z-score of -1. So that means that 27 would have a z-score of 1, and 21 would have a z-score of -1, because 27 is 3 above the population mean, and 21 is 3 below the population mean. Notice how these standard error bars are smaller than they used to be. That's because each bar is now 3 instead of 4. Since the standard error went down to 3, this entire sampling distribution became less spread out. In other words, it moved in closer to the population mean of 24. In an earlier video, we talked about how sampling distribution becomes less spread out when the standard error goes down, and that's just what we're noticing right here. Now let's look at how that's going to affect the margin of error. When the sampling distribution is normal, like it is here, the 70% of the possible samples always fall between these two z-scores. 15% always fall down here, and 50% always fall down here. That hasn't changed. But notice how these two boundaries are closer to the center than they used to be. That's because the standard error went down to 3, and each of these bars is now smaller than it was before. So 1.04 isn't as far out this way as it used to be, and negative 1.04 isn't as far out this way as it used to be. That means that if we wanted to calculate the 70% margin of error, like we did last time, the 70% margin of error would be smaller because the distance from the population mean to these two boundaries isn't as big as it used to be in our last example. Let's calculate the 70% margin of error and see what happens. We plug in this confidence coefficient, which is the coefficient for the 70% margin of error, and then we multiply by our standard error, which is right here. If we did that math, it would come out to 3.1. So the 70% margin of error is 3.1, which is smaller than it was last time we calculated the 70% margin of error. Now, why would we care that the margin of error went down? When the margin of error goes down, it means that the sample mean is likely to be more accurate, because less error is expected. If this 70% margin of error had been a big number, then this middle 70% area would have been really wide, and all I would know is that I have a 70% chance of my sample mean falling somewhere inside that wide area. I wouldn't be confident that my sample mean would be very accurate. But when the margin of error is small, like it is here, I know that I have a 70% chance of my sample mean falling inside a narrow area near the population mean, and I can expect my sample mean to be pretty accurate. If we went ahead and calculated some other margins of error, like the 80% or the 95%, we would see that those margins of error would also be smaller than they were before, because when the standard error goes down, the whole sampling distribution moves in closer to the center. It becomes less spread out, which means that each of the different margins of error becomes a shorter distance. Let's actually calculate the 80%. Let's actually calculate the 90% margin of error and the 95% margin of error just to see how they're smaller than they were last time. Remember that if the sampling distribution is normal, these are the boundaries of the middle 90%. So we're going to take this z-score at the upper end of the middle 90% and plug it in right here, and then multiply by the standard error to get the 90% margin of error. It comes out to 4.9, and that is smaller than it used to be. The reason why is because since the standard error went down, the z-score has changed. Everything moved inward toward the center, which means that these two boundary z-scores are closer to the center than they used to be. And if we calculated the 95% margin of error, it would also be smaller. It's 5.9. So overall, what we can see is that when the population standard deviation is smaller, the standard error will be smaller. And when the standard error is smaller, the sampling distribution will be less spread out. And when the sampling distribution is less spread out, the margin of error is smaller, and less error is expected. Let's now take a look at what would happen if we raised our sample size. What if instead of selecting a sample of 4 people, we were selecting a sample of 9 people? Well, our standard error would change, because instead of being the square root of 4, this would be the square root of 9. The square root of 9 is 3, and 6 divided by 3 is 2. So our bigger sample size has caused the standard error to go down. When the standard error goes down, the sampling distribution moves inward, like it did here. It becomes less spread out. Notice how each of these bars is now really small. And when the sampling distribution is normal, it's always true that this area is the middle 70%. This area is the middle 15. Sorry. It's always true that this area is the middle 70%. This area is the lower 15%. And this area is the upper 15%. But now each of those areas has become smaller because the sample means in the distribution have all moved inward. So when we plug this value in to get our 70% margin of error, we're going to get a really small number, or a smaller number than we did before. Now the 70% margin of error is only 2.1, which means that my sample mean is likely to be pretty accurate. When I randomly select the sample of 9 people from this population, I have a 70% chance of getting a sample mean within 2.1 of the population mean. If we calculated the 90% margin of error, it would also be smaller. So this is telling me that when I randomly select my sample of 9 people from the population and calculate the sample mean, I have a 90% chance of getting a sample mean within 3.3 of the population mean. So my sample mean is likely to be pretty accurate. And if I calculated the 95% margin of error using this confidence coefficient of 1.96, the 95% margin of error would also be fairly small. So this is saying I have a 95% chance of getting a sample mean within 3.9 of the population mean in this study over here. So overall, if the population standard deviation is small, or if the sample size is large, the standard error will be small, and the margin of error will be small, and you'll be likely to get an accurate sample mean. So when you're taking a random sample from a population, you're using the sample mean to estimate the population mean. You either want the population standard deviation to be small, or you want your sample size to be large, so that your standard error will be small, and your margin of error will also be small, and you'll be likely to get an accurate result.